coming in, but let's start now. And this event is for high school students, university students, college students. There will be hands-on session in the afternoon. So students are welcome. If you did not bring your son or daughter, next time please, then come with a laptop, because the success of the event depends on how good students are learning, how you are proposing solutions. So please bring someone or yourself, do some programming in the afternoon session. So the format of this event, we are part of Big Data Science event. Only a few days back, we had another main event where we bring in experts from industry only, who will talk about big data implementation solutions. And we had some people from Mirantis to talk about OpenStack and Ambari and so on. But this one is having a component which is about hands-on session. So there is a little difference. And here we will move into applications which are popular in ICT industry for mobile and pervasive computing. What kind of algorithms do you use, and what will be done in the back end? Do you need some interesting machine learning algorithms? How can we optimize them? So, and can we mix and match with machine learning algorithms? Things are rapidly changing, and something that we know may not be valid tomorrow. I mean, people are combining decision tree algorithms with k-mean clustering, support vector machines with partitioning. We will talk about all those things. There may be more implications for more rigorous mathematics. We can explore all of that. So we have to implement, we have to be satisfied what we are talking about, that is correct or not, and then build applications. And there are, hundreds of thousands of applications for ICT industry, starting from education, government, healthcare, hospital, and general customer segmentation. Name about anything. You can have a mobile phone and run something, and they are all ICT applications. So here we are. We have an open group in LinkedIn. It's called Big Data Science Universe. It's open group. Please become a member of that so that we can all collaborate, make some suggestions, and give us a date, time, sponsor something, suggest a speaker. So that's the nice collaboration platform. The meetup website, meetup.com, big-data-science, that is also there. But you have to send email to me or leave a message. But on LinkedIn, it can be all online. When you send a message or put a comment, we can reply back immediately in half an hour or so. So become part of that. And then I am one of the organizers. For the last 2.5 years, we did this. We went to Hadoop Summit 3 times. We were sponsored by Hortonworks and Yahoo. And we had very successful Hadoop Summit events on machine learning and mathematical shape of big data that happened in 2014 in June. So we are very, very visible. A lot of people know about our event. They want to come, and we had the top people like Ted Dunning from NAPAR. They are the people who contributed to Mahout and Storm and so on. They all came. They were speakers, and we are connected to many startup companies, Alpine Data Labs, many. I mean, look into our list, Cloudera, Hortonworks, they are all our sponsors. So Hawaii is our sponsor, that's why we are here and doing this. And there are lots of activities in Hawaii in big data space, so we will explore this. And our event host is Sippy Grant. She is the event manager of Hawaii. She's at the back. You can send her email also, c.grant@hawaii.com. If you have any questions about who can come, who cannot come, what can you bring, just send email to her. So what should we do in this particular meetup? We have 2 meetups every month. So in this meetup, we are going to discuss about general machine learning algorithms. So the thing is, what do we know about machine learning? Well, we know about support vector machines. Lots of startup companies, big companies, IBM, they all have implementations. And look into the applications, SVM is applied. It's from all over the place, from cancer genomics to talk about cell site buying or customer segmentation. Everywhere SVM is applied. It's widely used, and we have to understand that we can apply it in specific applications for ICT and so on. Then we have k-mean clustering. It's about given a data set, how the data is clustered around different mean values. So there we know about only one mean value for a set, but we can have k-mean values, and that we can find out by parallel executions on Hadoop platform, and it's a very popular machine learning algorithm called k-means clustering. Now that decision tree learning is another algorithm which is used heavily in cancer genomics, finding genes and so on, highly complicated, dealing with billions of records. So this has a pretty good list of applications also. Decision tree algorithms can be combined with k-mean clustering or SVM also to have more interesting machine learning solutions. And then we are focusing on ICT applications, as I mentioned, but we will look into more complicated applications with Internet of Things, IoT, that everything will be automated, industries will have sensors, homes will be automated, there will be smart cities, so we don't know how much of data will be collected. There may not be all data centers available to keep all the data. So how do we store the data, what kind of machine learning algorithm we apply? The main idea is to find statistical patterns so that we can optimize industries or supply chain or manufacturing activities. So that's a big place that we have to solve a lot of problems with machine learning. And then of course cancer genomics, everything is happening, and there will be more interesting implementations. So we will focus on Java, Scala, Python programming, and you go to Google and just do search for anything. There is code available, open source revolution happening. Everything is open source. The whole Bartlett data stack, Spark, Sharp, machine learning laboratories, Spark SQL, everything is open source. You go to Mahout, it's open source. Everything is open source. People are checking in their contributions. So open source is a revolution, and unless we know which open source package does what, we cannot use them. So we will get to know different packages for all these machine learning algorithms, how easily we can use them and build it with our applications. And so in this event we will have a talk, 1 hour talk, that will be generally about the overall strategy for a particular machine learning application. Say for example today the stress will be on decision tree learning, and then in the afternoon it will be like a connected thing that we do some exercise on decision tree. How do they look like? How we can build a nice machine learning app and so on. But you have to keep in mind that we have all kinds of students here also. So we will talk about some experts level of decision tree application you can explore with, or we can start from scratch. Even how to install Eclipse, we may have to do that and then start from there. And then please, you are welcome. Please send me email. My email address is there in the first slide. That's my email address, sarkar@bigdata@gmail.com if you want to speak. If you have a suggestion, if you know someone in the industry working on that, because this is how it will be more valuable, all these experiences, and get into this software exploration. This is all. And today's event, we have only one session, and our speaker is Dr. Sanhita Sarkar. She is co-organizer of this meetup, and she will talk about machine learning for ICT applications from 11:30 to 12:30. After that, we will have lunch break, and in the afternoon from 1 to 3 p.m. we have hands-on program. Having said that, I will give it to Sanhita to start.
So good morning, everyone. I'm Sanhita Sarkar. I'm the co-organizer of this meetup. As the other organizer already mentioned, so this meetup is focused on machine learning techniques, ICT applications, cancer genomics applications, and data sciences. And we definitely encourage students to learn these techniques and apply to real-world applications, as well as speak about their projects by applying these techniques. Similarly, we also invite industry experts to help out with hands-on sessions for the students. So with this, I will start talking about machine learning for ICT applications. So as many of us are new to ICT, I will provide an overview about ICT, its domains, its current trends, R&D needs and challenges, and then I will talk about ICT applications. After that, I will jump into machine learning, its basic concepts and models, and then I will focus more on the use of decision tree learning model for ICT applications. So there are other models that the other organizer talked about, like k-means clustering, support vector machine. So in future presentations, I will detail more on that for ICT. So today's presentation again will be focused on decision tree learning for ICT. So I'll start with the ICT overview. So what is ICT? ICT stands for Information and Communications Technology. So everyone knows about information technology, about telecommunications. But ICT is the unification, that's the unified communications, integrating telecommunications, computers, enterprise software, middleware, storage, audiovisual systems, which enable users to access information, store, transmit, and manipulate information. These are the various domains of domains and functions of ICT, and the various R&D needs corresponding to these domains. The first is sensors, abbreviated by S. Here the R&D needs really focus on developing tools and methodologies to acquire observations and then convert these observations into information for analysis. The other domain is communication, abbreviated by C. Here the R&D focus is to develop or enhance usability and the features of networks for reach and richness. The other domain is the databases and information systems, abbreviated by DBIS. So here the R&D needs are to design and implement global databases so that we can span all kinds of media, because database is a data store of all types of data. So the lot of focus is on NoSQL features, in-memory features, so that we can expedite the analytical capabilities as well as can meet the challenge of varied data sets. So also the capability of finding context in the information is one value-added feature for a database. The other domain is controllers, actuators, and effectors, abbreviated by CTRL. So here the focus is on designing robust control systems so that the effectors can perform their actions like robotic components with the help of actuators like the motors. And the other domain is human-computer interaction, which is HCI. Here the R&D focus is to design systems for managing and interfacing with ICT, like smartphones, handhelds, all-in-one devices, etc. Now, all these domains really fall under the umbrella of Internet of Things, which is evolving into Internet of Everything in the next few years. So what is the real-world impact of all these domains? So that I talked about sensors, communication, databases. What is the real-world impact? So one is infrastructure development, which helps in urban transport, electricity load management, water management. The other is basic human needs and development, like disaster and weather forecasting, warning, health monitoring, remote medical diagnostics. The other impact is economic development, like expanding markets in rural areas, and also helping in selling traditional or local goods. The other impact is empowerment, that is expanding e-learning, e-governance, supporting digital libraries, and also enhancing national and global inclusiveness. That I can reach anyone, anybody can reach me. So how do we really measure this information society? That is, how well am I really performing in order to impact the real world? So the United Nations International Telecommunication Union has come up with an agreed upon index called ICT Development Index, or IDI. This is based on certain indicators, so that this acts really as a valuable tool for benchmarking the various indicators, as well as compare performance, ICT performance, within and across different countries. So there are 11 indicators in 3 clusters, like readiness, use, and skills. So the readiness implies the capability to support infrastructure for deploying ICT technology. For example, number of fixed telephone lines, mobile telephone lines, international internet bandwidth, number of households with computers, households with internet. The use means intensity of ICT usage in a country or across different countries. That's number of internet users, fixed broadband users, mobile broadband users. And the skills imply the literacy and the openness, as well as the expertise to even deploy ICT. So these are the various indicators. Now, these are the development trends for where the benchmarking has been done with respect to various indicators. So this shows the growth of various indicators from 2001 to 2011. The highest growth rate is in the mobile area, mobile usage area, where you can see that there is a decrease in the landline usage across the years, which is really true. And this shows the top 30 countries ranked by their IDI. So this is real data benchmarked for all these indicators for all these countries. So these are some of the ICT applications broken down by application segments. First is public administration, where we have e-government and e-democracy, where the government can interact with people via internet kiosks, where there is universal access of information for the public. There's e-democracy, like e-vote, online voting. For urban and rural development, like e-services and e-information to the public. Transport, for smart cars, where we use sleeper cars for AC transit, for Caltrains. Then air transport control, freight monitoring. In the medical field, we have online healthcare, e-prescriptions, robotic surgical tools, SMS alerts. Then we have health portals, online health portals, where the medical providers can directly interact with patients instead of even requiring a face-to-face interaction. Then the education, we have online training, online EDUs, discussion groups. In the telecommunication area, we have network devices, amplifiers. And in the information systems, we have ESS or executive support systems, like what-if analysis is done by pilot in the cockpit panel. MIS, that is Management Information System, is summarizing all the information. DSS, Decision Support System, and for low-level analysis using business intelligence tools for low-level analysis. KMS, Knowledge Management System, sharing information for collaboration. TPS, Transaction Processing System for online billing, payroll, purchasing. Office productivity, that you are using VPN software and you are using software on your desktop. These are for productivity software for local and remote employees. So, but there are always challenges. So the challenges of ICT, one is digital divide, definitely by social, geographic, language, culture. So these are these types of divides really impact awareness and openness to adopt ICT. Availability and accessibility is definitely it is impacted, like whether we have access to the infrastructure to deploy ICT. Affordability even to buy the infrastructure and set up the ICT systems. So we see that the ICT opportunity is driven by the knowledge of ICT, and which is really impacted by the information and access of the ICT systems. The other challenge is reliability and robustness. So how are these I talked about so many engineering systems, how these systems are really reliable? What is the uptime? Do we have pipeline high availability? So these are key challenges that for ICT systems like intrusion detection device. Then content and contextual information. So to find context in all the observations that our sensor is doing, to find context in the data and to make it comprehensible for the public, that's another key area of focus, which is a challenge. The other challenge is security and governance. Are these intrusion detector systems really secure? Are these algorithms that are being embedded in these systems, in the smart devices, how much are they secure to really detect false positives, false negatives? And are we able to reduce these false negatives and false positives and provide proper security to the public? So these are the challenges and these are the areas where a lot of research is going on, and machine learning techniques can be really applied to these various ICT application domains that I talked about to solve some of these challenges. So now I will move on to machine learning, the basic concepts and models of machine learning, and how machine learning can be applied to ICT use cases. And today's presentation will again focus on the decision tree model instead of other models. In later presentations, I will focus on other models like k-means clustering and support vector machine. So what is machine learning? As everyone knows, machine learning refers to the construction and study of systems that can learn from data. So for example, we have an email system which tries to distinguish between spam and non-spam messages. So after some iterations of errors, it tries to improve its performance. So that's the reason it is a learning system. So it improves its vision via learning. So that's the machine learning system. Now, machine learning also allows for performing predictions based on known properties or a training set. For example, you have a training data set, you apply machine learning algorithm and you create a hypothesis, that's a prediction, which may not be accurate. Then you apply that hypothesis to test data and you measure your performance of your prediction. So based on that, based on the feedback, you improve your algorithm. So that's the reason it's a learning system. There are two types of these broad categories of machine learning models, the supervised and unsupervised learning. For supervised learning, you already know the categories or labels to classify, which I will go in details in the next slide. And in unsupervised learning, you don't know the categories, but you have to try to find those categories. So here, for example, in supervised learning, you have one bag of salmons, one bag of sea bass. You build a model, and then you are given a mixed bag. You know what criteria to use for classification. Here you have to classify with the type of fish. Then in the supervised case, unsupervised case, you are given a mixed bag. You have to build a model. You are not given the criteria to find the classification. You are given another mixed bag. Based on the learning from the first iteration, you have to try to classify for the next mixed bag. So here you don't know the category for classification. Some examples for supervised learning is that you predict cancer in a patient based on some labeled data from the patient. So you already know the various symptoms of cancer patients. Based on that, you are predicting whether this patient has cancer or not. So you have some input training data set. Similarly, for sales forecast, given the 3-year sales revenue, you are trying to predict the next 5 years of sales revenue. For unsupervised learning, example, you are asked how many different factors are available that cause cancer. So here you don't know where to start with, how to categorize it. Will you start by geography, by gender, by type? You don't know. So this is one example. Other is market basket analysis. So you don't know where to start, what things to classify to find the customer's buying pattern in a grocery store. Is it dairy, non-dairy? Should I start with tobacco, non-tobacco? So in these types of unsupervised learning, we use association rules. Like bread is associated with butter. When a customer buys bread, the customer is most likely will buy butter. So this is an association will be used in market basket analysis for predictions. So these are some of the machine learning models. So first is the supervised learning. Under the supervised learning model, we have some algorithms like linear regression. where you have a set of independent variables, and you can find the values of dependent variables based on the values of the independent variables. Then you have the decision tree. You have a set of a full training set given to you, and you are also know what to predict, the target attribute to predict. The other is naive Bayes. So here you have multiple input features, and you have to, and these input features are naively or strongly independent of each other. This is a Bayesian theory. And an apple is a fruit. So this prediction is based on many input features. The apple is red, apple is sweet, apple is round. So all these features are independent of each other to make the decision that apple is a fruit. So this is Bayesian theory. Next is the support vector machine. So in the support vector machine, we already know the classes to classify, but we will have to find the biggest margin or the gap between the classes. So that is the optimization problem of support vector machine. Next is unsupervised model. So first is k-means clustering, where we are given the number of classes, but we are not given the category for classes. So we start with an arbitrary classification, and then we try to find the most convergent mean in these classes. So that's the optimization problem. The other is mixture models. Here we try to find probabilistic distributions of subclasses or subpopulation out of the total class or population. For example, we can use exponential distribution, like yes votes out of the total number of votes. So that's a binomial distribution. We can use exponential distribution, like what's the probability that the event will happen at this particular time, given that the event really changes at a fixed rate. The other is association rule, as I mentioned, like ham and cheese is really associated with bread. So when a customer buys ham and cheese, most likely the customer will also buy bread. So this is an association rule used in market basket analysis. The other type of machine learning model is reinforced model. So like, for example, Markov decision process. So the reinforced learning is something like a decision maker decides at a stage S whether to take an action A or not. If he takes an action and is successful, he gets a reward. So this type of learning is instantaneous. You decide at a particular stage. So we use these types of learning in robotics. The robotic movement is decides at a particular state in automated cars and automated chess players. So the other is semi-supervised learning, like graph-based methods, where there are many input parameters which are unlabeled, which are unknown, but there are some which are known. So for example, in a social networking graph, many of the input parameters are unknown, so it's so complex, but some are known. You know some of the attributes, the values of some attributes, but not all of them. So to find patterns in social networking graph is so challenging because of this unlabeled, the variety of unlabeled data sets. Now I will talk about decision tree learning for ICT applications. So as I already mentioned or described, decision tree is supervised learning. So it is a tree-like graph to display a classification model. So here each internal node or a non-leaf node is a decision node which corresponds to a test on an attribute. And the outcome of the test is a branch. And the leaf nodes are the classifiers, classification labels. They contain the actual classification. And the root node is the topmost node of the tree, which is the first decision node when I start building the tree. So this is an ICT application like predicting commute time on a smartphone. This is an ICT application like which is used in the information system for traffic management. So for example, we have a problem statement to predict. For example, if we start at 10 a.m. in the morning, what will be the commute time? So we have some known facts from the training data set, like there is heavy traffic as usual during office hours, less traffic is usual after office hours, and during an accident or a stall, lanes are closed, and that will lead to long commute time. So these are known facts from our training set. As we work with the environment, we know all these facts. So based on that, we create a decision tree and create some rules out of that. For example, if hour is 8 a.m., definitely it's during office hours, so commute time is long, which is 2 hours. Else if hour is 9 a.m., so a little bit later, then if there is an accident, then the commute will be 2 hours, else commute time will be medium, like 1.5 hours. If hour is equal to 10 a.m., which is after office hours, then if there is a stall, these lanes are closed, then commute time will be long, 2 hours, else commute time will be 1 hour. So we build a decision tree, so we see that if we leave at 10 a.m. and if there is no stall, then only it is the shortest commute time. So this type of rules we can embed in a smartphone, and when we get the real-time traffic feeds, we can make dynamic predictions on a smartphone. So this is an ICT application. The other application is like predicting sport event days. This is an ICT application for weather information system for e-sport. For example, the steps for building a decision tree, these are the steps. First, we try to identify what are attributes to really measure, what attributes are really measurable. That's like outlook is one, with possible values sunny, cloudy, rainy, temperature, hot, mild, cold, humidity, high or normal, windy, true or false. We then choose a target attribute to predict, like soccer event. So it's whether it's feasible to play soccer, have to have a soccer event on those days or not. So that's the attribute to predict, yes or no. And then we create a sample table out of that. So these are the various values. This acts like a training set for the tree to be built. Then we build a tree out of that training set. So we first choose the best attribute to split. So that to find the best attribute, there are some calculations to be done, like finding the entropy and information gain, which I will go through the next slide. But first, after we find the best attribute, this is the step I'm describing. First, you find the best attribute, then you try split it with the values, and then you go to the next level of the tree and follow the same process, finding the best attribute at level 2. So this is a recursive process, and you stop building the tree when you don't have any more attributes in the training set. You run out of attributes, and you are done building the tree. Now these steps follows an algorithm, which is ID3 algorithm by Quinlan. With this uses entropy and information gain to construct the decision tree. So these are the steps. First, you determine the attribute that has the highest information gain on the training set. So that becomes your root node. And then you create a branch for each of these values that the attributes can take. For each of these branches, you repeat the process with the subset of the training set that is classified by the branch. So it's the same process you apply for the branches. Now, how do I really measure that the attribute is the best? So that's the challenge. So you have to know what entropy is and how to calculate information gain. So what is entropy? Entropy is a measure of disorder or impurity. Suppose you have a sample and you have 50% positives and 50% negatives. So it's totally an impure sample. So entropy is 1. It's totally impure. If you have a homogeneous sample of all identical items, then entropy is 0 because it's fully homogeneous. So you can see that to calculate the homogeneity of the sample, the metric is called entropy. Now this is the formula to calculate entropy. So if we have p theta plus proportion of positive samples in a training set and p theta minus negative samples in a training set, then the formula of entropy is minus p theta plus log of p theta plus minus of p theta minus log of p theta minus. So all the logarithms are to the base 2. Now information gain is the reduction in entropy. So it is the entropy of level, in simple language it's the entropy of at the tree level n subtracted from the tree level n minus 1. So as the level of the tree increases, the entropy reduces and the information gain should increase. That's from your test results, you should expect this kind of result. So this is a graph which is actually derived from real experiments that we have done. And this is, you will see that as a decision tree level increases, you will see that increase in the information gain and a reduction of entropy. So how do we calculate the entropy for the attributes using that formula that I showed? So this is a real world example from the soccer event, the table that I showed earlier. So here the number of positive samples is 9 and the number of negative samples is 5. So that we plug in this formula, this was the formula, so we plug in this formula and we see entropy of the soccer event is equal to entropy minus of the p theta minus, which is proportion of negative samples, that is 5 by 14, that is 0.36, log of 0.36 minus of 9 by 14, which is 0.64, log of 0.64. And we calculate the entropy as 0.94. Now, if you have another attribute, that was just one attribute. If you have another attribute like outlook, then this is the formula where we plug into this formula and say, like for the soccer event, we have the another attribute like outlook, which has the values sunny, overcast, and rainy. So what will be the entropy of soccer event outlook? There are two attributes here. Will be the probability of the outlook to be sunny multiplied by the entropy of the soccer event over the positive and negative samples for the outlook to be sunny, plus our probability of overcast multiplied by the entropy of the soccer event for the overcast to be positive and negative for the soccer event to generate positive and negative results for the soccer event attribute, plus the probability of the rain outlook to be rainy multiplied by the entropy of the soccer event to have positive and negative outcome when the outlook is rainy. So we plug into this formula and we use the entropy formula for this values, and then the ultimate entropy is 0.693. So the information gain will be 0.94 minus 0.693, which I describe in the next slide. So how do we now calculate? So we got the entropy values for different attributes to calculate this way, and how do we calculate the information gain? So here we calculated the entropy, as I mentioned, 0.94. Now in the step 2, I have to decide which attribute to pick to be the root of the tree, where I will start the split. So I have to calculate the entropies of the information and the information gain for all the attributes. So here, these are the attributes. One is outlook, temperature, humidity, and windy. So where should I start? So I calculate the entropy, which I already showed here for the outlook and soccer event. My entropy here was 0.693. The information gain is entropy of soccer event minus entropy of soccer event outlook, which is 0.94 minus of 0.960, which is 0.247. So the information gain for this attribute is 0.247. Similarly, I calculate for the other attributes, temperature, humidity, and windy, and I see that the information gain for the outlook is the maximum. So this becomes the root of the tree. Now this is how I start building the tree. So I pick this outlook as the root. The outlook has three values, sunny, overcast, and rainy. For the overcast, we see only one branch, which is homogeneous branch, as entropy is equal to 0. Here, this is because for all the values of temperature, humidity, and windy, if the overcast or if the outlook is overcast, then it's true. The soccer event is always true. So this is the single branch, and we come up with a leaf node. And for the other branches, like for the other attributes like sunny and rainy, for example, for sunny, the entropy is greater than 0 because it has two mixed values. Like windy can be false and true, and the soccer event varies according to that. So we fill this tree accordingly. So this way we recursively do that, and we build the tree ultimately. So this is the final tree. We use a similar process for rain. So the decision tree here also helps to create decision rules in an information system. For example, from this decision tree, you can write some rules like if outlook equal to sunny and windy equal to false, then we should have a soccer event. So these types of rules can be embedded in a smartphone, and again, as I mentioned, we can get dynamically we can get the weather information and we can plug it in and we can do that in real time. Here we can use some threshold values like sunny is equal to 70 degrees Fahrenheit. So these are some threshold values we can even use in those rules in the algorithm and plug it in an expert system. It will be like an expert system. So what is decision tree pruning? So decision tree has some issues. For example, the biggest issue is overfitting, the one big issue. So that's the overfitting actually happens when you have many attributes with many values. So the tree becomes very large and complex. And the ultimate predictions of the classification that it provides is a noise. So, and it has poor predictive power. So that is one symptom of overfitting. The other is that the tree memorizes the training set, and it cannot generalize sometimes with unseen circumstances, unseen data. If you give new data set, it provides poor predictions because it has memorized the training set. So if you use the tree for a training set for a long time and you have not enhanced it with new data set, it happens. So to alleviate all these problems, we usually use pruning technique. So what we do, we try to delete some of the branches, sub-branches of the tree, so that we have a better predictive power of the tree. So these, some of these branches, we pick those branches which do not provide any valuable information or is causing error or noise in the prediction. So here, for example, this is a tree T and this is a node T. So we want to prune this tree or delete all the successor nodes of this node T. So we delete, this is the deleted tree, and this is the prune tree, T/T, where the small t is now the leaf node of the tree, of the primary tree. So pruning here is a technique in machine learning that reduces the size of the decision trees by removing sections of the tree that provide little power to classify instances. So why do we do this is to reduce the complexity of the tree, because now we have smaller number of classes to deal with, it's more manageable, and it has more predictive power. And because we have reduced the noise out of the tree, those nodes that are causing the overfitting. So we have better predictive accuracy for this tree. So the actual goal of decision tree modeling is to find the smallest tree with the highest predictive power. So these are some of the real-world applications which really are using decision tree today. One is in astronomy, where decision trees are used to filter noise from cosmic ray hits in Hubble Space Telescope images. They are used for star galaxy classification. In biomedical engineering, decision trees are used to identify features in implantable devices. Also, the automatic induction of decision trees are used to build robust control systems. In financial analysis, decision trees can be used to find or to predict the attractive buy rights in stock trading. In manufacturing and production, it's used in semiconductor manufacturing for on-demand material procurement, for statistical quality control. In medicine, it's used automatic induction of decision trees, like in a medical expert system you build. Their decision trees are used in diagnosis, cardiology, psychiatry, gastroenterology, and also analyzing sudden infant death syndromes. In molecular biology, it's used in human genome project in a very big way, analyzing amino acid sequences. Like you try to classify the protein coding sequences from the non-protein coding sequences. Then for object recognition, tree-based classification is used to recognize three-dimensional objects. In pharmacology, it's used for drug analysis. In physics, it's used for detection of physical particles like quarks. Also in power systems, it's used to predict security and stability of power systems. For remote sensing, it's used for tracking frequent visitors in a store and their buying patterns of the customers. Sensors are used and decision trees are used for remote sensing, and as well as for very large data sets in earth science, which really contain large class, high dimensional data. Also, decision trees are widely used in security, like classification of strong and weak passwords, in spam filtering, in intrusion detection systems, classifying false positives, which is false alarms, false negatives, like missed signals, true positives, like attacks, and true negatives, like normal traffic. Also, it's used in software development for estimating the development effort of a given software module. Also, it is used in a medical expert system to classify medical text. And there are other miscellaneous uses like building personal training assistance and classifying sleep signals. Now, how the decision tree can be implemented in a big data architecture. So you can use Hadoop MapReduce. You can trigger MapReduce jobs to build decision trees. So there's a lot of research going on in Stanford, and this is an excerpt from a Stanford University presentation in 2014. In around February. So here the master node, you have Hadoop cluster, you have master nodes, you have data nodes. So the master node is the primary controller for the whole building of the decision tree and managing the decision tree. Here it triggers the MapReduce jobs as well as controls the training model, the decision tree model, also the attribute metadata, and also tracks the intermediate results. So the master is the primary controller which tracks the whole model and decides how to grow the decision tree. So these are the processes, the whole process in steps. One is the one thing to remember is the tree is built in levels. It's built one level at a time. There's one MapReduce job to build one level of the tree. The master decides which nodes and splits to consider. So what are the possible values where I can create that split that the master will decide. And then it triggers the MapReduce jobs, and the MapReduce, actually the reduce function which I will show, will compute quality of these splits. Then it provides the feedback back to the master. The master will grow the tree for a particular level. And then you go to the next step, which is the next level of the tree, it starts again. So it is an iterative process until unless you complete building or going through all the attributes of the tree for splitting, and you build the tree, and ultimately the master will build the final tree. So here, this is the build architecture, the decision tree build architecture on Hadoop. So the tree is again built level by level. There's one MapReduce step which is built for one level of the tree. There's one MapReduce for one level of the tree. Here the master will tell the mappers which splits, which nodes and which splits to consider. Then each mapper will guess the subset of that data, and it will compute the partial statistics for a given split. It will calculate the rules for each of these attributes. And then the reducers will collect these partial statistics and output the final quality for a given split. Here the reducers actually calculate the entropy and information gain to calculate to derive the best split from all the splits provided by the mappers. And then it provides a feedback to the master, and the master makes the final decision where to split. And the master then grows the tree for one particular level. So these are the various MapReduce components. The master monitors everything. It triggers multiple MapReduce jobs. And these are the MapReduce jobs. This is a MapReduce initialization. That is, in the training set, the first MapReduce step is initializing. You read the training set, find out which attributes to pick, you identify, and then which possible splits are really meaningful. So that's the first, it runs only once, and that's the initialization process. And then there are multiple times the master now triggers the MapReduce jobs to find the best split for each level. So these are done multiple times, and then after that, when the master gets all the values of the best splits, it finally builds the tree in memory. So it's a decision tree analytics on the big data architecture. This is a kind of overall system architecture that I just mentioned, where the master gives the mappers the tree, the set of nodes, set of candidate splits. The mappers collect that data and provide the key value, output the key value pairs like the node ID, the node number, and the split value, And the reducer then calculates the purity or the output, and it outputs the best fit by calculating the information gain. So there is one blog where you can find the Java code for that. So here if you can try it at home. So here there is Java code already available to calculate entropy and information gain. So you can there are some examples, and here there is you can click on this to really download the full source code and try it. So this is a decision tree performance. So after you really do that, so there is some research.
So I'm assuming will you get a copy of these slides?
Yes, we can put it in SlideShare.
Okay, because I can record the URL there.
Okay. I think we have sent it already. We have sent it to the meetup group.
Okay,
It's in the comments.
Oh, got it.
Events.
Okay.
So this is the decision tree performance graph. Some researchers in China has done real benchmarking of decision tree on Hadoop architecture. And this is an excerpt from the International Journal of Database Theory and Applications in 2014. This is a very recent publication. So here it shows that the whole experiment has been done with different sizes of training data sets, 0.5 million, 1 million, 1.5 million to 3 million. So it's done on Hadoop with 8 nodes. So it's seen that the best speed up really happens with 3 million records, 3 million instances of MapReduce instances in a training set. So why that is happening? Because it's the largest data set is giving the best speed up. The reason is that in a Hadoop architecture, when you have a very large data set, the bigger the data set, the denser is the distribution on the data nodes. As a result, you will have less communication overhead between the nodes. And if you use 0.5 million on 8 nodes, the data will be sparse. And when you are doing reduced jobs, there will be a lot of communication overhead. So that's the reason that the Hadoop is really meant for big data. And when you have a very large Hadoop cluster architecture or very large infrastructure, please try to use very large data sets so that you can have the better performance. So that's the key message. And so thank you for listening to this presentation. If you have questions, there is lunch. If you have questions and you want to discuss further, we can do that during the hands-on session. Thank you.
Do you have any questions, please? Going to come to the...
No. Can you explain the notion of master?
Master?
Master.
So in a Hadoop cluster, there is a master node. Master nodes comprise main node and secondary main node. The job tracker was in Hadoop version 1. Now there is no job tracker, so it's resource master. So these are the master nodes. So the name node plays a key role in managing the metadata of all the data nodes. It contains all the information or all the key value pairs for all the data nodes. So that's the master node of Hadoop. So if you can run the master program in the main node. Because that way you can read. Pardon?
Pruning them on a different data set?
Yeah, different data sets that are not. So pruning is done on the already built tree. You get the training set, then you build the tree, then after a long time when you are not enhancing the training data set or you are not really looking into the predictive power or the tree starts getting older and it tries to memorize the training set. So you don't prune the training data set, you prune the tree. You chop out some of the nodes in the tree, which is causing noise, which is not valuable anymore in classification, not providing any value in your predictive classes and in your predictions that you already asked it to do. Then you chop that. So that's called pruning. So you prune on a tree.
Can you explain a little more how you do that?
So I already described that. How I do that means when there is, for example, I described overfitting. So when you do that is one thing, and how you do that is you delete that portion of the tree. So that's I showed you. I can go back then.
you start with the first layer, first level of the tree, or on the leaf?
No, you have to go into the level where you want to prune the tree. So that level,
How do you
like
identify
n minus.
How do you identify the subtree problem?
Yeah, the subtrees are problem is because the classification, the leaf nodes, I find it out from the leaf nodes. If the leaf nodes are not meaningful classes, for example, suppose you have like dairy, non-dairy, some of the other classes I showed, sunny or windy that I showed you. The windy is the wind, for example, the windy attribute, the leaf nodes that is classifying true or false. That whole part of the tree is not important anymore in prediction. So you chop out that whole windy subset of the tree. Let me show you this here, for example.
So actually a follow-up question on this is, then how is the pruning of a tree different than pruning of a data set? Because you're almost saying that if the windy is, for example, in this example, windy is not important, you're kind of getting rid of all the training set which was windy.
Yeah, the rules with the windy. Yes, you are getting rid of that part, but without building the tree, you will not know which data set to really, from which attribute from the training set to really cut it out, because you don't know the predictive power of the training set. That is the original training set. So you have to build a tree to get the prediction.
So I want to add something. Windy or sunny or rainy, they are everywhere in all the records, maybe. Now this is the meta information is in the decision tree, and there the classification may have windy or not windy, sunny or not sunny, and windy may be 0.05% of the whole set. Then that is not very meaningful for the whole knowledge or the knowledge discovery or whatever. So you can prune that also.
Because it is a learning method.
So you are not taking out the records. You are not deleting the records. You are deleting the knowledge in the decision tree. Some parts not making any sense.
It's a model or a metadata representing the training set. So you are not deleting the real data is there, but you are deleting the knowledge or which is providing the prediction. Because it's not there.
Automatic or
No, you have to do that. It's not automatic.
But
you have to rewrite in the
there's a criteria sometimes when you get that.
When you are
So if the percentage of sunny days are 80% or more, then whatever is 20% or less, you can prune them. Something like that. So there can be some decision. Right.
The pruning always means tree rebuild. So you start to do it again.
Pruning means the tree will become skinnier.
You have to do the calculation on each node again.
Right. Information gain and
not all the nodes all over again in that level.
at the
Like for the windy, you know you have calculated the information gain earlier. You have the tree, you know it because you built it. So you have the knowledge of the information gain. But right now you are seeing that due to windy, that particular activity, you are getting erroneous predictions. Why is it happening? You go and try to investigate which level of the tree and which attribute is meaningless and what is really causing the error. So you have to find that out. So that's the reason it's learning process. You have to keep on enhancing the tree.
So each node is independent. Once you remove one, does it have any impact on the other
No,
nodes?
yeah. So we have to remove the tree so that yes. So you have to remove the tree carefully. That will not affect the performance of the whole. The log n is the height of the tree, and that's the cost complexity of the analysis, decision tree analytics. So you have to make sure by removing the tree you don't make it n log n. So then.
A couple of things, just a comment. You didn't say anything about the height of the tree. Decision trees are well known that
Yes,
they are
it's log
cool
n.
when the height is large, because probability becomes bizarre. So that's one comment. The other one, whoever did this experiment, have they tried to do it also using Spark rather than, map reduce on Spark rather than Hadoop to see how fast it is? Or?
Yes, so right now people are doing, I also want to do it as I am the part of the R&D division in Hawaii. So I'm also wanting to do creating yeah, so I'm trying to also build a strategy to do that. So Spark here, it uses the HDFS and it has MLlib. MLlib is used as a part of the Spark. So right now it's still in development. How far the MLlib, the decision tree algorithm MLlib is robust to be used. I am not sure because I have not tested
but
it.
this thing here implemented MapReduce, the decision tree was
Yes.
implemented MapReduce. So I'm saying, have you tried to do the same thing for Spark to see the response time difference? I expect to be.
We can do that because it's in memory, it can be cached in memory. The whole, if you have enough memory in the node for like a node today maximum is 384 GB. So if you can fit the data in memory, you can use the Spark and you can cache the data and build the data fully in memory. Yes, that is possible, but I have not tested that.
Because I think actually I'm guessing is what you're trying to say is the metrics which are shown here may be different when it's on Spark versus MapReduce.
That's right.
Yeah, that is possible. So Spark MapReduce, yes, people are still like in March and April we have the first paper out, decision tree on MapReduce. That itself is complex. Now to use Spark on MapReduce for the decision tree, yes, that is one other project that is good to do, and we can that will be another paper definitely to even compare the performance of different models.
Actually, when you use Spark, you will not use MapReduce, right? These are alternatives.
That's right. We will not use MapReduce. So they claim we are seeing that it's 100x faster than MapReduce Spark, but I did not see it in my own experience. I saw around.
Spark support many paradigms, including MapReduce.
It does?
It's up to you. Yes, it does. It goes to support SQL, support streaming, support many things. So that definitely is there. The other thing is, yes, Spark is in-memory memory processing, but they actually allow you to do overflow because they understand they have
To
weaknesses.
spill the data
You
to
can
them.
spill
Yes,
the data.
yes, that's
So the question is, how much
of data.
How much gain you get with the in-memory processing if the data is even larger than what you can fit.
And if it is terabytes of data, then it may not be able to fit in memory. At that time there is a, yes, that is the experiment I really want to do. What is the best strategy or best practice to use the Spark, and how much of data really you need to address with Spark?
As you know, in the industry, there's a lot of debate about if Spark is going to replace Hadoop or not. Right, I mean, it's a very hot topic. It would be nice, I don't think it will replace it, but I think it would be very good to understand when's appropriate to use this versus that. That's really what I feel.
Now the thing is, the problem with Spark is that it has to have some connectivity over competing units, and that doesn't work once you are out of that Spark cluster. So, for example, scalding, cascading, and all those things, the new packages written, they don't work on Spark because the way pipe is defined, logical pipe, Spark doesn't support that. So when you are talking about IoT and the data coming in zettabytes, in the data centers are overflowing, probably Spark or no Spark, that doesn't matter.
I agree, but if the data can fit in stream processing, Spark will win big time.
Yes.
Because it's not the size of the data anymore, the stream, the throughput, primarily what you care about.
It's still in development. I'm not seeing wow performance yet in the initial testing. So yeah, so I'm hearing that ML for machine learning algorithms will be more supported. And how much decision tree, what's the performance of decision tree with ML versus MATLib versus other tools we are trying to test.
It may be a little bit silly question, but in the experiment, I see up to like 8 processors with Hadoop. Are there like typical numbers of like Hadoop to show like performances? Because it could be like thousands, not.
Oh, 8 is very small. 8 is very small. Yes.
I think that this algorithm will fail in the master node because master node will get all this information. So if it becomes big, like if you have certain processor, it may not scale too. I'm just wondering.
So master node is, the main node is never a bottleneck because it only maintains the metadata. It's not really dealing with the full data set. Data is always on the data nodes, always in the Hadoop cluster. And that is one thing. And the other thing is that yes, 8 node for if you run Cloudera, for example, 8 node is minimum. But if you run like, from our own experience, for our 8 node cluster, 100 GB to 500 GB will run very well. After that, 1 terabyte, it will start getting slow because you will have network bottlenecks. if you have a 10 gigabyte, so you have to have a 10 gigabyte switch. The switch is very important. Your full switch architecture is extremely important for having not just the nodes. Number is not the most important thing. Networking is very important in how you create the network architecture. So
So the master don't worry about detail of each node, all details are
yeah, mainly you have to focus on the data nodes, the number of drives, the number of memory, whether you have the right proportion of memory versus your cores as well as the drives. So if your CPU's cores are only like 12, not only, of course, 6 core per CPU, you have 12 cores, and you have only 8 drives or 4 drives, then you will see I/O bottlenecks because there will be wait times for the I/O completions. So if you can have a proper ratio of the number of drives with the number of cores for parallel I/O for IOPS, for the best IOPS which you need to measure even before you properly install the Hadoop. Before you install, you must take all these measurements, whether your IOPS for your cluster is good enough to address the complex problem, and for a 10 terabyte data set, for example, then you have not.
I totally agree with what you said, but let me add something here. You need to understand that Hadoop will not work well with small data sets. We did an experiment, for example, all these machine learning algorithms are implemented in one machine used by universities. Library called Wig, very popular one. And believe it or not, you have 4 to 8 nodes and small data set, like 20, 50 gig, you can write 100. Wig on one CPU complete the job faster than Hadoop. Hadoop, something ugly has something ugly for shuffle, and that will slow down the RAM. However, when you go beyond that, we're around few gigabytes, but when you start paying, you cannot handle it. So it's really Hadoop is meant for large scale. It is great at that time because Hadoop is far more improvement. But that one is not responsible. So keep that in mind when you work. Big data and you care about throughput, not response time.
Hadoop is not for response time.
That's correct.
Yeah.
You building the tree at each node, you compute the entropy and information you consider each node which feature is put on, right?
Yes.
So you declare as each node, is it a separate MapReduce task?
Yes, so that's why I showed you the best split that's done by the reducers. So the mapper sends the partial stats, the partial values to the reducer then calculates. So these are the mappers gave me these split values, then I calculate the entropy information here, and it gives the feedback of the best values to the master. The master then decides which has the maximum, and that will really, master will always decide which attribute to pick for the split for the next level.
So in the sense that total number of MapReduce tasks are the number of nodes?
No, it's always not equal to the number of nodes. MapReduce is definitely less than the total number of nodes. There is a formula for doing the MapReduce. It depends on the number of cores you have per node. Because everything, the MapReduce jobs are run on the data node. Number of cores, suppose you have 12 cores, and you have enough memory, like around 256 GB memory per node. Then you have to make sure that you have the config file, that XML config.xml file in your Hadoop cluster, and you have to configure that so that the MapReduce tasks, number of tasks, is not more than 12, for example. So you start with a number, and then you go ahead, and in your memory, that's heap, that the heap amount per process, per MapReduce job should not exceed the total memory of the node. So those calculations you have to do, and this is a tuning process.